Hi, so we are going to cover properties of logarithms, section 8.5. But you're probably looking at what's on the whiteboard and you're like, wait a minute, that's not in my notes. And it's not. We're going to do something slightly different that is actually going to help you understand these properties better than if we were to just read through a list of them. So what I want you to do as we go through everything on the whiteboard here is don't take notes. I do not want you to take notes. I want you to just listen, think, understand. So the way this works is we're going to start with this very first row. And I want us to think about if we evaluate this very first example here. So log base 5 of 5. And I'm asking the question, if I take that base of 5, what exponent do I need to raise it to in order to equal that argument of 5? So 5 raised to what exponent is going to give me 5? Well, that's just 1. Let's look at the next one. It's very similar. 2 raised to what exponent gives me 2? Well, that's going to be 1. It doesn't matter if we have a base that's a fraction or an argument that's a fraction. The process is the same. Log base 1/2 of 1/2 is going to be equal to 1. So you should be thinking now, what is that pattern that I saw? Well, as long as the base of your log is the same as your argument, then that logarithm is going to evaluate to 1. Okay, that is your first property. Now, let's look at our second row. And so this one, let's start the same way, okay? We're asking ourselves, 5, that base of 5, raised to what power is going to give me 1? Well, remember the definition of a 0 power exponent. So if I have a variable raised to the 0 power, it's always going to be equal to 1. As a matter of fact, if I have anything raised to the 0 power, it's going to equal 1. So log base 5 of 1 is going to be equal to 0. That's what my exponent is here, a 0. Let's look at log base 2 of 1. So that's saying, what would my exponent need to be in order to equal 1? Well, that's going to have to be 0. If I've got log base 1/2 of 1, it's going to be 0. As a matter of fact, anytime your argument is equal to 1, then your whole logarithm is going to be evaluated to be a 0. Let's go to our next row. So for this one, I've got log base 5, and my argument is an exponent, 5 to the 3rd. So if I set this up in exponential form, it would be 5 to the question mark is equal to 5 cubed. Well, because my bases are the same, then that means my exponents need to be the same. So that question mark must be equal to 3. That means that whole thing gets evaluated to be 3. All right. So now let's look at the next one. 2, I can do that above it. 2 raised to what power is equal to 2 to the 5th? Well, my bases are the same, so my exponents have to be the same. That means that question mark must be equal to 5. Doesn't matter if I have fractions introduced. Log base 1/2 and then 1/2 to the 4th is going to be equal to 4. So the pattern that we see here is when our argument is an exponent, and when the base of our log and the base of that exponent are the same, then that logarithm is equal to that exponent of k. Let's look at this last one. So I've got an exponential form, 5 raised to the log base 5 of 25. Well, let's change that exponent to logarithmic form. So I know that the base of my log is going to be 5. So I can rewrite this as log base 5 of something. Let's just put x equals that exponent log base 5 of 25. Using the concept of equivalency, as long as our bases are the same, they're both on both sides of my equation. I've got a log base 5, log base 5. So that means my arguments must be equal to each other. This x has to be equal to 25. And so that means this exponent is going to get evaluated as 25. Okay? Let's see for the next one. The next one is going to be equal to 16. Because if I turn that into exponential form, from exponential, convert it to logarithmic form, it would be log base 2 of x is equal to log base 2 of 16. And so x has to be equal to 16. For this next one, 1/2 raised to the log base 1/2 of 1/8. That is going to be equal to 1/8. So I think you see the pattern. When you have something in exponential form and your exponent is actually a logarithm, as long as the base of your exponent and the base of your log are the same, then that exponent is going to be equal to k. Okay. All right. Those are your first 4 properties right there. So now let's go on and we're going to investigate a little bit deeper. So let's go ahead and start with this first example. So log base 2 of 8. Well, okay, that is going to be equal to 3 because 2 to the 3rd is equal to 8. Log base 2 of 4. That is going to be equal to 2 plus log base 2 of 2 is 1. So I've got 3 is equal to 2 plus 1. Now, let's kind of go back to the beginning here. What if that 8 had actually been expressed as 2 factors, 4 times 2? Let's keep that in the back of our mind as we now look at our property. So the product property for logarithms tells us that if we have log base A of x times y, okay, then we've got log base A of x plus log base A of y. We take those two factors, we create two logs in which we add those logs together, and they have the same base as our original log. Now let's look at a quotient. Here's an example. So log base 5 of 125 over 5. Well, let's just simplify this. 125 over 5 is going to be 25. So log base 5 of 25 is 5. Now, log base 5 of 125 is going to be, well, I can take that 125 and I could change that to 5 to the third. So using my properties, because the base of my exponent and the base of my log are the same, that's equal to that exponent of 3. I actually, how did I get a 5 up here? I don't know. That should have been a 2. 5 squared gives me 25. Was I thinking? Okay, now log base 5 of 5, that is going to be equal to 1. So 2 is equal to 3 minus 1. So when you have the quotient property, what you're really doing is you're going to create two logs, but you're going to subtract them. So that's going to be, let me start over here, log base a of x minus log base a of y. Last one. This is called the power property for logs. So applying my properties of logs, when my base of my log and the base of the exponent are the same, that's equal to that exponent, 3. Okay? Now, if I pull down this 3 and then multiply it times log base 4 of 4. So when my base and my argument are the same, that's equal to 1. Well, that's a true statement. 3 is equal to 3 times 1. So the way the power property works is you take this exponent and you put it in front. So it's going to be P times log base A of x. All right, let's go. Now that we've kind of got that really strong understanding of what these properties are, let's go apply them. So, where did it go? There we go. So here inside of this yellow box are the first 4 properties that we just spent time going over. So I'm not going to go over them again. They're exactly the same. Only thing is this should say logarithmic form. All right, so now let's use these properties inside the yellow box in order to evaluate 1A, B, and C. And so we're going to start with, let's organize myself here. When I look at this first log, this first equation here that I want to simplify. So I have got my base of my log and the base of my exponent are the same. And so this is going to be equal to the exponent of x. Plus, anytime your argument is a 1, then this log will evaluate to be 0. So this becomes x plus 0. That's just equal to x. Let's look at the next one. So for this one, I've got, right here. I'm going to go ahead and log base 3 of 3. My property tells me that is going to be equal to 1. Then I'm going to subtract when my bases are the same, the base of the log and the base of the exponent, it's equal to that exponent of 3. So 1 minus 3 equals negative 2. Let's look at C. So for this one, okay, I've got, it's in exponential form, but the base of my exponent, the base of my log are the same. And so this is equal to 7 minus the base of my log and my argument are the same. So that is equal to 1. 7 minus 1 is 6. Okay? So I applied my properties to simplify each of those expressions. Now, let's go ahead and what we're going to do, we've got now in this yellow box all 7 of our properties. And we're going to use our properties to do what is called expanding our logarithmic expressions. And so this is going to be the first one. Couple things. First of all, when my argument is a fraction, okay, that means that I am going to subtract I'm going to create 2 logs and I'm going to subtract the top minus the bottom. Okay? So I'm going to subtract. So that is going to be log base 5 of 3x minus log base 5 square root of y. Okay? Second thing that I'm going to do is I see here with this first log that I have 2 factors as my argument. So I am going to add, I'm going to create 2 logs that are added. Okay, so that's going to be log base 5 of 3 plus log base 5 of x. Now, with this next log, what I'm going to do, okay, is I am going to convert my square root to, oh, you can't read that. I'm going to convert that square root to a fractional exponent and use the power rule. Okay? So, so that's going to be, so minus log base 5 y to the 1/2. Now, this 1/2 is going to come in front. So that's going to be minus 1/2 log base 5 of y. The other 2, I can't do anything with them, my other 2 logs. So I'm just going to copy them over. Log base 5 of 3 plus log base 5 of x. This is the expanded form of that log. Okay? All right. Let's do, oh, there we go. They're exactly the same thing. So now let's do this next one right here. Okay? So first thing I see is it's a fraction. So that means I'm going to subtract top minus bottom. So that's going to be log base 4 of 3x minus log base 4 of 64. So I see with my 3x. So the first thing I did was subtract. Now what I'm going to do is I am going to add with the first log. So this 3x can be separated into 2 logs. So log base 4 of 3 plus log base 4 of x. Next thing I'm going to do is I am going to change 64 to exponential form. That is going to be 4 raised to the 3rd. So that'll be minus log base 4 and then 4 to the 3rd. Well, okay, couple things I could do. I could apply the power rule, take that 3, put it in front, or I could just recognize from my original 4 properties that when the bases are the same, that log is going to evaluate to that exponent. So then my final answer is log base 4 of 3 plus log base 4 of x minus 3. And then that one is done. All right, let's look at this next one. We'll use a different color. So this one's a little bit more interesting. Again, we start here that we've got a fraction bar. So whatever is in the bottom is going to be subtracted, whatever's in that denominator. So let's just make that our first step. Log base 7 of x squared y minus log base 7 square root of z. So these first 2 factors, okay, the factors that are in that first log, they can be separated, and the way we do that is by using our product property of logs, and that makes us add those 2 together. So that's going to be, didn't want this, log base 7 of x squared plus log base 7 of y minus, while I'm at it here, I'm going to convert that square root, that radical, to fractional exponent. So I'm going to put log base 7 z to the 1/2. Okay, so now what I can do is apply my power property. So this 2 is going to come in front, and this 1/2 is going to come in front. So my final answer is going to be 2 log base 7x plus log base 7y minus 1/2 log base 7z. There we go. It's all good. Let's do C as another example here. All right. One of the things before we go into C that you should be noticing is that, or one of the questions you should be asking yourself is, why, when I have factors, do I create 2 logs that are added? Why don't I multiply those 2 logs? That's a reasonable question to ask. But I want you to think back about what a log is. A log is an exponent. And so the reason why we add those 2 logs is because of the properties of integer exponents. Recall that when you have the same base, so x to the m being multiplied by x to the n, you don't multiply those exponents, you add them. That's exactly why we're adding them here. When you have like bases and it is set up in a quotient, okay, you don't truly divide the m and the n, you actually subtract them. That's why we're subtracting when it's set up as our argument is a fraction. Okay, so now that you kind of have that deeper understanding and how it all links back to integer exponents, let's move on with this next problem. So I've got here a fraction bar. So I'm going to set this up as log of base 5, x to the 6, square root of 5, minus, we'll just leave it like that, minus log base 5 to the 17. Okay. Oh, I wrote that wrong. I can see why I wrote it that way, but I wasn't paying attention. It's log base 5. That part was right. But my argument should be 5 to the 17. Makes a huge difference. All right, so now let's start with this first log. I have two factors that are being multiplied. So I'm going to add them. Log base 5, x to the 6, plus log base 5. I'm going to change that square root of 5 to 5 to the 1/2. Okay, minus log base 5 of 5/17. Okay, so now I can apply the power rule. I can apply it here. I can apply it here. I can apply it here. Okay, so this is going to give me 6 log base 5 of x, okay? Now, when I take and put the 1/2 in front, I'm left with log base 5 of 5, which is 1, okay? So that's like multiplying 1/2 times 1, which is just 1/2. The same thing happens when I put that 17 in front. I get log base 5 of 5 again, which is 1. All right, so now only thing I need to do is take 1/2 minus 16, which is a negative 16.5. So my final answer is 6 log base 5 of x minus 16. You could write 16.5. You could do 16.5. You could put it as an improper fraction, 33/2. Those are all acceptable. All right, let's do D. This will be our last example of expansion. So one of the things I want you to notice is notice how I've got this square root or this radical, which encompasses my entire argument. Before, when we had radicals, they were just one of the factors. Now it's the entire argument. Well, how does that work? Well, okay, the very first thing we're going to do is we're going to convert that radical to a fractional exponent. So I'm going to rewrite this as log, and that 5 is my index of 5. It's not a base 5. This is actually a base 10. So it's just log, and then I'm going to put parentheses with the 1/5 on the outside. And then the 2 over xyz is my argument. Now I'm going to take this 1/5 and pull it out front. So this is going to give me 1/5. Oops, why did I write? I said 1/5, but wrote 1/2. 1/5 log 2 over xyz. All right, now I can do my expansion. So this is going to be 1/5, but watch what I do. I'm going to put a square bracket in order when I do my expansion. So this will be log 2 minus log x. Now watch this. For every factor that's in the denominator, I'm going to put a minus. So minus log y minus log z. Well, why in the heck did I do that? Well, let's kind of do a little aside here. If I had log base 2 and I had my normal, let's subtract our denominator, that would be log x, y, z. Okay? Let's keep those parentheses there. So that'd be log base 2 minus log x plus log y plus log z. All right, now when I distribute this minus sign, it's going to flip the sign of each of those logs inside of the parentheses. So you end up exactly with what I have written here. As a matter of fact, you can skip all those pink steps and just recognize that when you have factors in the denominator, every single one of them is going to have a subtraction sign in front of that log. You can go directly to that step. Saves you a lot of work. Now, I'm going to go ahead and I am going to distribute this 1/5 to every one of those logs. And so that's just going to give me 1/5 log 2 minus 1/5 log x minus 1/5 log y minus 1/5 log z. That is done. That one was fun. Okay, now we're going to go the other direction. We're going to start with it in expanded form and shrink it down to a single log. Most people find this pretty intuitive, okay? So we're going to work backwards. Anytime you've got subtraction signs, that means that argument is going to go in the denominator, just for the reasons I said in the last example. Second thing, anytime you've got a coefficient, that is going to become the exponent of that argument. Okay, so my base of my log is not going to change. This is still base 19. Because I have subtraction signs, I know that my argument is going to be a fraction. Anything that is positive and like a positive log, meaning no subtraction sign in front of it, that is going to go up in the numerator. Okay, so I've got 17 to the 1/4. In the denominator, I have y squared times x. The only thing I'm not really loving here is that fractional exponent. So I'm just going to go ahead and change that to a radical. So this will be log base 19. There's my fraction bar. I'm going to make a radical where my index is a 4 and put the 17 inside as my radicand. Then I've got y squared x. That one's done. All right, let's do another one. Okay. So this one, I'm going to go ahead. I see that I have one subtraction sign. So that means my log is going to be, my argument of my log is going to be a fraction. So I'm going to write log base 5, because my bases are all the same, put my fraction bar. This 3 is going to be the exponent of the first part of my argument here, so x cubed. And then this 9 is going to be the exponent for that y, so that'd be y to the 9th. In my denominator, this 1/2 is going to be the exponent for the z, so z to the 1/2. Again, not loving that I've got a fractional exponent, so I'm just going to change that. So log base 5 x cubed y to the 9th square root of z. Done, done, done. Okay. Let's look at this next one. Now, for this one, couple things to notice. First, I've got a subtraction sign. Then I also want you to notice that this is an improper fraction. That should be a red flag that I'm going to have to do some extra simplifying of a radical at the end. All right, so let's go ahead and set this up. My base is the same for all those logs. It's base n. I know I'm going to need a fraction bar. The first factor in my numerator is going to be 5 to the 1/4. Then I'm going to have x to the 2/3. And in the denominator, I'm going to have z to the 5/4. Well, I've got some work to do here. I need to go ahead and convert all of those fractional exponents to radicals. So this will be log base n, then the 4th root of 5 times the cube root of x squared. Those are all good. Those are simplified because my exponents are smaller than my index. So I'm good. In the denominator, when I convert this, I have the 4th root of z to the 5th. So for this one, my exponent is larger than my index. So that means I can simplify that denominator. As a matter of fact, if I take the 4th root of z to the 5th, I can change that to the 4th root of z to the 4th, z to the 1st. So when my exponent and my index match, that means I can take out a root of z. So that'd be z, 4th root of z. That's what I'm going to substitute in there. So my final logs simplified as a single log is going to be in my numerator 4th root of 5, cube root of x squared, and then the denominator is going to be z times the 4th root of z. All right. One extra one that I want to do because you're going to see it on homework, okay? And it's not like any of them we've done. It's actually easier, but it might not seem easy because you haven't seen it before. So I see that with the orange highlight that I am going to have an argument that is a fraction. So it's going to be log base 3. Then in the numerator, I'm going to take 54 times 10. Those are my factors. In the denominator, I'm just going to have 20. Now, I can actually simplify right here, okay? 10 goes into 20 2 times. 54 divided by 2, that's going to give me 27. This is crazy. So this is going to give me log base 3 of 27. Well, 27 is the same as 3 cubed. So I can change this to log base 3 of 3 cubed. That's a lot of 3's. Okay? When the base of the log and the base of the exponent are the same, this is equal to that exponent of 3. All right, so now you should have enough information to really have fun with this homework.